And the fundamental challenge of the Raptor 3 is not just the management of heat, but the prevention of a catastrophic chemical reaction between the engine's own structure and its propellant. In the previous section, we explored how liquid methane acts as a thermal buffer, whisking away the brutal heat of combustion. However, regenerative cooling is only half the battle. On the other side of the engine, the side driven by the oxygen-rich turbopump, we encounter a problem that transcends simple thermodynamics and enters the realm of aggressive chemical warfare. And in the high-pressure environment of the Raptor 3 oxygen pre-burner, we are dealing with a gas-phase oxygen environment at pressures exceeding 300 bar. At these levels, the laws of chemistry begin to behave in ways that seem alien to our terrestrial experience. In a standard atmosphere, a piece of steel is a structural material. In the high-pressure, high-temperature oxygen stream of a full-flow staged combustion engine, that same piece of steel is something else entirely. It is a highly concentrated fuel. And the oxygen-rich nightmare when metal becomes fuel. To understand why SpaceX had to develop its own proprietary superalloys, one must first appreciate the oxygen-rich nightmare. In most rocket engines, like the Merlin or the Russian RD-180, the turbine is driven by a fuel-rich gas. This is because fuel-rich gas is relatively inert toward the metal components of the pump. However, the Raptor 3 full-flow staged combustion cycle requires one of its turbopumps to be driven by a stream of hot, high-pressure, nearly pure oxygen. And in this environment, almost every metal known to man will spontaneously ignite. If a single microscopic particle of dust or a tiny shard of metal, known as FOD or foreign object debris, strikes a traditional nickel alloy turbine blade at supersonic speeds, the resulting friction provides enough activation energy to start a fire. But this isn't a fire that burns on the surface. It is a fire where the turbine blade itself is the wood. Within milliseconds, the entire turbopump, a masterpiece of precision engineering, literally turns into a puddle of slag and is ejected out the nozzle as engine-rich exhaust. And for the graduate-level engineer, this is a problem of oxidation kinetics. At the pressures found inside the Raptor 3, the chemical potential of oxygen is so high that the protective oxide layer, the passivation layer that prevents stainless steel or aluminum from rusting away in your kitchen, is stripped away or bypassed entirely. We are no longer designing a machine. We are trying to contain a continuous, controlled explosion using a container that desperately wants to join in the explosion. In SX500, the metallurgical kernel-level security patch. To solve this, SpaceX moved beyond the off-the-shelf solutions provided by the aerospace industry's traditional favorites, such as Inconel 718 or Monel. While these alloys are impressive, they were never designed for the specific, violent intersection of high-pressure oxygen and extreme mechanical stress. The result of SpaceX's internal research is SX500, a proprietary superalloy that represents a pinnacle of metallurgical alchemy. And in the language of computer science, if the engine's software handles the logic of the flight, SX500 is the kernel-level security patch. It is a fundamental hardware-level fortification that prevents system corruption. In this metaphor, the oxygen-rich gas is a malicious exploit, a viral force seeking to find a vulnerability in the metal lattice to trigger a runaway reaction. SX500 is the hardened hardware that remains inert even when the exploit is running at full capacity. And consider the analogy of the unburnable paper. Imagine a sheet of paper that you could place inside a blast furnace, pump in pure oxygen, and blast with a blowtorch, yet it refuses to catch fire. It doesn't just resist the heat, it refuses to participate in the chemistry of combustion. This is what SX500 achieves within the Raptor's oxygen pre-burners and turbopumps. It provides a structural substrate that is chemically indifferent to the presence of high-pressure oxygen. And the trade-off, strength vs. conductivity, designing an alloy like SX500 is a masterclass in managing conflicting requirements. In the world of materials science, you rarely get something for nothing. Usually, there is a brutal trade-off between three primary variables. And high temperature yields strength, the ability of the metal to hold its shape while being spun at 30,000 RPM at temperatures where most metals are the consistency of taffy. Oxidation resistance, the chemical nobility of the metal, its refusal to react with oxygen. Thermal conductivity, the ability to move heat through the metal to the cooling channels. And a material like copper has world-class thermal conductivity, which is why it is used for the liner of the main combustion chamber, the part that actually touches the flame. However, copper is structurally weak. If you built a turbopump out of copper, it would fly apart the moment it reached operational speed. Conversely, materials like tungsten have incredible heat resistance, but are brittle and nearly impossible to manufacture into complex geometries. SX500 is a nickel-based superalloy, but its specific doping with elements like cobalt, chromium, and other proprietary refractory metals allows it to sit at the Goldilocks point of this triad. It is strong enough to handle the massive centrifugal loads of the turbine blades, yet it possesses a chemical immunity to oxygen that allows the Raptor 3 to run at higher pre-burner temperatures than any engine before it. And by increasing the allowable temperature in the pre-burners, SpaceX can increase the pressure of the entire engine. This is the full flow advantage. Because the metal can survive more heat, the gas can be more energetic, meaning the pumps can spin faster, which increases the chamber pressure, which ultimately increases the thrust-to-weight ratio. SX500 is the enabler of the entire thermodynamic cycle. And metallurgical alchemy, the microstructure of resistance. What makes SX500 different from a standard high-performance alloy? The secret lies in its grain boundary engineering. And when metal solidifies from a liquid to a solid, it forms grains, microscopic crystals that fit together like a 3D jigsaw puzzle. The boundaries between these grains are the weak points of the material. In a high-pressure oxygen environment, the oxygen atoms try to wedge themselves into these boundaries, causing intergranular corrosion. Once the oxygen penetrates the boundary, it begins to unzip the metal from the inside out. SX500 is engineered to have a specific crystalline structure, often involving single crystal casting or highly controlled directional solidification that minimizes or eliminates these vulnerable boundaries. For the graduate reader, this is analogous to memory alignment in high-performance computing. Just as a programmer aligns data to memory boundaries to prevent cache misses and page faults, SpaceX engineers align the crystalline structure of the metal to prevent oxidation faults. And by controlling the orientation of the atoms within the turbine blades, they ensure that there are no low-energy paths for oxygen to follow. The metal becomes a solid, monolithic wall of resistance. This is not just a material. It is a geometry of atoms designed to repel the intrusion of the environment. And the dry advantage and the role of the superalloy. As discussed in the previous section, the Raptor 3 is a gas-to-gas engine. This means the propellants entering the main chamber are already vaporized. However, the path to that vaporization is where the superalloys do their heaviest lifting. And in the oxygen turbopump, the liquid oxygen enters at cryogenic temperatures and is compressed to staggering pressures. It then passes through the pre-burner, where a small amount of methane is added and ignited to turn that liquid oxygen into hot, high-pressure oxygen gas. This hot oxygen is the most corrosive, most dangerous fluid in the history of rocketry. And if the internal surfaces of the turbopump were made of standard aerospace alloys, the dry nature of the gas would actually make things worse. Without a liquid film to provide a slight cooling effect, the gas would find every microscopic imperfection in the metal and begin the combustion process. SX500 allows the Raptor 3 to operate dry. It removes the need for complex inert gas seals or purge systems that other engines use to keep oxygen away from vulnerable metal parts. In the Merlin engine, for example, the turbopump is a single-shaft design that requires a complex ullage space and seals to ensure the fuel and oxygen never meet. In the Raptor 3, because the metal itself is oxygen-proof, the design can be much more integrated and compact. This is the zero-trust architecture of the Raptor 3. The hardware doesn't trust the propellant, so it is built to be inherently immune to it. And structural integrity under mechanical violence. Beyond chemistry, we must address the mechanical violence of the full-flow cycle. The turbopumps in the Raptor 3 generate tens of thousands of horsepower, enough to power a small city, all within a component the size of a V8 engine. And the turbine blades in the oxygen pump are subjected to creep, a phenomenon where metal slowly deforms under constant high stress and high temperature. If a turbine blade creeps even a fraction of a millimeter, it will strike the housing of the pump, causing a spark event. In a high-pressure oxygen environment, a spark is a death sentence. SX500 is designed with a high gamma-prime volume fraction. This is a secondary phase within the nickel matrix that acts like rebar in concrete. These microscopic precipitates pin the dislocations in the metal's atomic structure, preventing them from sliding past one another. This gives the Raptor 3 internals a temporal stability that is unmatched. The engine can be fired, cooled, and fired again hundreds of times without the metal forgetting its shape. And for the systems engineer, this is the hardware equivalent of idempotency. No matter how many times you run the execution, the engine firing, the state of the hardware, the dimensions of the turbine, remains unchanged. This reusability is the cornerstone of the Starship program, and it is made possible not by the flight computer, but by the precipitates in the SX500 alloy. And the problem of thermal expansion and the copper superalloy interface. While SX500 handles the oxygen-rich nightmare in the pumps, the main combustion chamber presents a different challenge: the interface between the heat-conducting copper and the load-bearing superalloy jacket. And as the Raptor 3 heats up, the copper liner expands at a different rate than the outer structural jacket. This is a thermal expansion mismatch. If not managed, the copper would buckle or pull away from the jacket, leading to a failure of the cooling channels. And SpaceX uses a proprietary bonding process, often involving electroforming or vacuum brazing, to fuse these disparate materials at the molecular level. This creates a gradient material where the properties of the engine wall change as you move from the fire side to the structural side. In Layer 1, the fire side, a specialized copper-silver zirconium alloy that can handle the massive heat flux and conduct it into the methane channels. Layer 2, the structural side, a high-strength superalloy like SX500 or a related variant that acts as the exoskeleton, holding the 350 bar of pressure. And this is a multi-layered defense strategy. The copper handles the thermal packets, while the superalloy handles the pressure loads. If the copper is the front end that interacts with the user, the superalloy is the back end that provides the robust infrastructure. In the manufacturing bottleneck, why proprietary matters, you cannot buy SX500 on the open market. You cannot even find its exact composition in public patent filings. It is a trade secret in the truest sense of the word. And the reason SpaceX brought this in-house is not just for performance, but for iteration velocity. Traditional metal suppliers in the aerospace industry operate on timelines of years. If SpaceX discovered a hot spot in a turbine blade during a test at McGregor, they couldn't wait 18 months for a supplier to tweak an alloy's chromium content. And by owning the foundry and the recipe, SpaceX turned material science into a software iteration cycle. They could compile a new batch of SX500, deploy it into a test engine, and debug the results in a matter of weeks. This metallurgical agility is what allowed the Raptor 3 to shrink in size while growing in power. The code of the engine is written in the ratios of cobalt to nickel. In conclusion, the substrate of ambition in the end, the Raptor 3 is a testament to the fact that you cannot solve the hardest problems in physics with software alone. You can have the most advanced regenerative cooling algorithms and the most precise boundary layer fluid dynamics, but if your metal catches fire in the presence of oxygen, your engine is nothing more than a very expensive firework. SX500 and its sister alloys are the silent partners of the Raptor 3. They are the reason the engine doesn't self-terminate during the transition to full power. They provide the immunity that allows the metabolism of the full-flow staged combustion cycle to function without consuming itself. And however, even the most advanced superalloys and the most efficient cooling loops are useless if they cannot be manufactured with absolute precision. The cooling vanes we discussed in the previous section, those thousands of micro-channels that carry the methane, cannot be drilled by any conventional machine. They are too complex, too small, and too integrated into the structure of the superalloy itself. And to bridge the gap between the theoretical metallurgy of SX500 and the physical reality of the engine, SpaceX had to master a new form of creation. This leads us from the what of the materials to the how of the construction, as we explore 5.4 the geometry of channels, 3D printing the cooling vanes.